Working on our review guide, numbers 13 through 23, all about series and sums. In 13 and 14, we're going to find the sum of the series based on the information we're given. Looking at the pattern we observe in number 13, we can see that this is arithmetic because we're adding 2 every time. So we know that the first term is 2. The common difference is also 2. And that the last term in the series we're adding is 70, but we need to know its position. We need to know how many terms we are adding together. So our first step will be to find where 70 is in the sequence so we know how many terms we're adding together. We go back to our arithmetic rule where the term equals our first term plus the common difference times n minus 1. And doing our algebra. Oops, excuse me. That should say 35 equals n minus 1. Sorry, 35 equals n. All right, so now we know we're adding 35 terms together. Because we know both the first and the last term, we can use the shorter of the two sum formulas for arithmetic series. We'll be finding the sum of the first 35 terms, which is n over 2, 35 over 2, times the sum of the first term plus the last term, which is 70. And we type that into the calculator, and our sum is 1,260. All right, in 14, this is another arithmetic series because we are adding 2. Our first term is 1, common difference is 2, and our last term is 59. But as with the previous problem, we do not know where 59 is. So our first step is to find where 59 is in the series. Based on our general arithmetic rule, our first term plus the common difference times n minus 1. And we'll be adding 30 terms together. And we can use the same formula that we did for the smaller of the two arithmetic sum formulas, because we know the first and the last term. So this time we're finding the sum of 30. Start with n over 2 times the sum of the first and the last terms. And the sum of those first 30 terms comes out to be 900. All right, we're going to identify the pattern that we see in 15 and 16. And we could put a 1 right here with our 2. And we notice that the numerator is 2 to an increasing power as we go through the series, and we're going all the way to the 14th. So we could write this as a geometric series, but it would probably be quicker to just write this in sigma notation. We're going to add the first term all the way through the 14th, and we can generate each term by raising 2 to the power of n over 4. And then we can go to the calculator and evaluate this sigma notation. Now we're using our TI-84 calculator to evaluate the sigma notation in number 15. That requires us to go to Math, scroll up or down until you find the sigma notation, hit Enter. And we're going to fill in our start, our stop, and how to generate each term. Remember to use x as your variable, the x key next to the alpha key. We're starting with the first term. You can use your arrow keys to navigate to the different parts that you need to fill in. We're adding to the 14th term. And the formula for generating each term is 2 to the power of x divided by 4. Once everything's set, hit enter. We do have a decimal. We can always ask our calculator to turn that into a fraction for us. So math, fraction, enter. And we see that the answer is 16,383 over 2. So that's one approach. In number 16, if you prefer, we can think about this as a geometric series because we are multiplying by 3 to get from one term to the next. So we know that our common ratio is 3. We know that our first term is 3/9. And based on the exponents that we observe from the 1st to the 15th, we are going to be adding 15 terms together. So you can use sigma notation. You can treat this as a geometric series. We're finding the sum of 15 terms in a geometric series. So our formula would look like this. And then we can go to the calculator to evaluate that sum of 15. We're now using the calculator to evaluate our sum in number 16. We've written this as a geometric series, geometric sum of 15 terms. So I'll start with 3/9, then our numerator. We get this answer, 2,391,484.333. So that's and 1/3. If we ask our calculator to turn this into a fraction, won't do it. I think the number is too large, but we can do it ourselves. I tried this with sigma notation as well. It also would not turn it into a fraction. So this is all in thirds. We're going to take the whole number, the 2,391,484, and we're going to multiply that by 3 to turn it into thirds. And then the decimal beyond that is an additional third, 1 additional third. So I'm going to add 1 to this number, and then we'll take this answer and put it over 3, and that's our answer expressed as a fraction. So we have 7,174,453 over 3 as our final answer. All right, as we move on to problem number 17, these are infinite geometric series. And the formula for infinite geometric series is the first term over 1 minus the common ratio. But we can only use this if it converges. And it will converge if our common ratio is less than 1, if our numbers are getting smaller as the series progresses. If it doesn't, then we're going to say that the series diverges and we cannot find the infinite sum. So as we look at 17, our common ratio is 1/2. Therefore, r is less than 1. This series converges. And we're able to find the infinite sum by plugging in our first term of 8 and our common ratio of 1/2, and that gives us an infinite sum of 16. In number 18, our common ratio is 4. Therefore, our common ratio is greater than 1. The series diverges, so we cannot find the infinite sum. In number 19, we need to look at the way the series is expressed with this formula here. 2 would be our first term, 3 would be the common difference. Let me strike that and repeat. 3 would be the common ratio, because we're dealing with a geometric sequence. And because our R value is greater than 1, then this sequence diverges and we will not find the infinite sum. In number 20, similar scenario, we have the formula for our geometric series right next to the sigma notation, and we're looking at a common ratio of -2/3. Because the absolute value of -2/3 is less than 1, then this series will converge. And we can find the infinite sum by putting the first term, which would be 6, over 1 minus the common ratio. Common ratio is negative, so you'll see there's minus a negative there. We're going to turn that into addition. And when we do that and simplify, we get that the infinite sum is 18/5. In our next three questions, we'll be taking a series and turning it into sigma notation. When we're expressing using sigma notation, we're going to see if we have an arithmetic series, if we have a geometric series, or if not. So as we're looking at the series in 21, there is no common difference. First we add 3, then we add 5, then we add 7. So it's not strictly arithmetic. There is not a common ratio from 3 to 6 and 6 to 11. So we're looking at this pattern where we're adding 3, and then 5, and then 7, and then we'd add 9, and so on and so forth. Which means we have to establish how we're going to generate 3, 6, 11, 18 explicitly from their position. So 3 is the first term, 6 is the second term, 11 is the third term, 18 is the fourth term, and so on. And if we are looking to transform these positions 1, 2, 3, and 4 into the numbers 3, 6, 11, and 18, we would need to square each position and then add 2. So that is our rule for how to generate each term in the series. And if we keep adding and we get out here to 83, this would be the 9th term. So we need to follow that pattern through so we know how many terms we are adding. So when we go to sigma notation, we're going to start with our first term. We're going to add all the way up to the 9th. And our rule for generating each term is n squared plus 2. All right, in number 22, we're still using sigma notation. We're going to look first to see if it's arithmetic or geometric. -1 to 1, 1 to 3, 3 to 5. We are adding 2, which makes this one arithmetic. And we're adding all the way to wherever 41 is. So we know that the first term is -1. We know our common difference is +2. And we know that the last term is 41, but in order to write sigma notation, we need to know where that term is. So we're going to use our arithmetic rule. 41 equals the first term plus the common difference times n minus 1. Oh, excuse me, I already added the 1. And we see there that n is the 22nd term as we solve. So when we write our sigma notation, we're going to start with the first term, and we're going to add to the 22nd term. And our rule for finding each term in the sequence is our arithmetic rule. That's in its non-simplified form, so you could also distribute and combine like terms. And once you distribute and combine like terms, that becomes 2n minus 3. So that is sigma notation for an arithmetic series. As we look at 23, 2 to 10, 10 to 50, we're not adding the same value, but we are multiplying by 5 every time. So our common ratio is 5. That makes this geometric. We know that our first term is 2, and we can see all of the terms. So we're adding to the 5th term, which is 1,250. So we have everything we need to write our sigma notation, starting with the first term, adding to the 5th. And because this is geometric, we'll just write our geometric rule next to the sigma notation, which is our first term, times the common ratio to the power of n minus 1. And those are our series, sums, and sigma notation problems.